Let's discuss gate 2005. Okay, question. So heat flows through a composite slab as shown. I'll draw the figure as shown below. The depth of the slab is 1 meter. The K values are in watt per meter Kelvin, and what is asked is the overall thermal resistance in K in Kelvin per watt is okay. So let me draw the figure what is given. So this is a composite slab. Q is going like this. Okay, K is 0.02. This width is 0.5 meters. This is 0.25, and this is same thing. 0.25. This depth is 0.5 meters, and the total is 1 meter. And this K is 0.1. This K is 0.04. Okay. So now let me just try to build. So let's try it on the option 17.2, 21.9, 28.6, 39.2. So let's do this problem, and so let's try to build up a resistance diagram first for this problem, because once you build a resistance diagram, everything else will be all very simple. So if I try to build a resistance diagram, as I already told you, in a conduction, the steady state temperature distribution through a slab is Ka T1 minus T2 by thickness, which I am denoting by L. This can be written as T1 minus T2 by L by Ka. So this L by Ka is nothing but the conductive resistance, and T1 minus T2 is delta T. So this is conductive resistance. So let's try to build everything in terms of conductive resistance. So this is my resistance, and then heat. So first the heat has to pass through this, and now there are two options. So it is something like this. So I can say that you have a series and then a two parallel network where heat gets distributed. Okay, so this is L1 by K1A, and this is L2 by K2A, and this is L3 by K3A. Okay, and what is asked is the overall thermal resistance. Okay, so let's plug in the values first. L1 is 0.5 by K1 is 0.02. Area of cross section is nothing but, for this the area of cross section is this into the depth. This is 1 meter and depth is 1 meter. So for the first slab, it is area of cross section is 1 into 1. Okay, so this is L1 by K1A, which is 0.5 by 0.02. So that becomes 25. And L2 by K2A is this slab. So this slab length is 0.25, conductivity is 0.1, area is this area of cross section is this into the depth. So this is 0.5 and the depth is 1. So this is 0.25, okay, by 0.1 into 0.5. So this can be written as 1 by 0.2. So this is 5. Okay, and L3 by K3A is same thing, 0.04 by K3 is K3 is 0.04, sorry, length is 0.25, and area is again 0.5 into depth 1. So this is 1 by 2, 0.04, this is 1 by 0.08, and that gets 100 by 8, which is nothing but 4 2s, 4 25s, this is 12.5. So this is my resistance. So once I put these values, the value which I get is this is 25, this is 5, and this is 12.5. So effectively these are in series, these are in parallel. So in parallel the resistances they add. So resistances for this would be, now in series they add, in parallel they follow a harmonic resistance. So these two, the R for the parallel will be R1 R2 by R1 plus R2. So it is 5 into 12.5 by 5 plus 12.5. So this comes out to be 62.5 by your 17.5, which is nothing but your 3.57. So that is your RP effective 3.57. Now these are in series, so the effective would be 25. So in series they add, so it's 3.57, so that is nothing but 28.57. So close to 28.6. So the units of this, as you know, it's Kelvin per watt. So the answer for this is 28.6, which is C. So problems like this, build up a resistance diagram, and then whether effective resistance is asked or interface temperature is asked as it was in the previous case, or the overall heat transfer is asked. So if the overall heat transfer is asked, you have to first get the effective resistance, and then if temperature difference across the slab is given, then use this relation delta T by effective resistance. But what is effective means overall here. Okay, let's discuss another question from GATE 2005. So this is a question on radiation. A solid cylinder S2 is located the center of a hollow sphere which is of surface 1. The diameter of the sphere is 1 meter, while the cylinder has a diameter and length of 0.5 meter each. The radiation configuration, which is nothing but your shape factor or the view factor, is asked. So the radiation configuration factor F11 is, okay, so 0.375, 0.625, 0.75, D is 1. Okay, so what is given? A solid cylinder surface 2 is located. So we have a cylinder is located at the center of a hollow sphere. So this is your sphere, which is surface 1, and this is your cylinder, which is surface 2. Okay, diameter of the sphere, length, everything is given. F11 is asked. So we use summation rule for each surface first, because I assume that everybody knows the meaning of radiation configuration factor, which we have just discussed in the previous. It's basically the fraction of energy that leaves a surface I and how much portion of that strikes surface J. That is given by Fij. So F11 means amount of radiation that is leaving surface 1 and striking it back. So summation rule for each surface 1, it will be F11 plus F12, because these are the only surfaces that are participating. So F11, so some radiation from 1 can strike it back like this, and some portion will strike it here. So F11 plus F12 is 1, and for surface 2, which is cylinder, is again F21 plus F22 is equal to 1. Now one more thing is that because it's a convex surface, so F22 for the cylinder is whatever leaves cylinder will not strike it back because it just moves radially outwards. So this is 0. Okay, and then you have the reciprocity rule, which relates the mutual shape factors. So A1 F12 is A2 F21. This is again from the reciprocity rule. Okay, so now what we want is, let's get what we want. A11 is what I want. For that I need to know F12. F12 is here, but for this I need to know F21. So can I know F21 from this? F22 is 0, so F21 is 1. So let's substitute it here. So F12 is A2 by A1 F21. Now A2 is cylinder, so cylinder surface area is pi, it's the total. Okay, so now because it's the total, so you have to include everything. So A2 is the cylinder surface area. It's a small inside the cylinder, so you have to include everything. So it's 2 pi r square for each end plus 2 pi rl for the lateral surfaces. This is A2, and your A1, which is the surface area for the sphere, is 4 pi r square. 4 pi, the radius of the sphere, r square. Okay, don't confuse with this and that. So this A2 by A1 would be 2 pi r square plus 2 pi rl. Well, length of the cylinder is equal to the radius of the cylinder, so this is also 2 pi r square plus this is 4 pi rs square. So this comes out to 4 pi r square by 4 pi rs square. That is nothing but becomes the radius of the cylinder by radius of the whole square. So radius of, I'm sorry guys, what mistake we have done is the diameter and the length are equal. Okay, so let's just recalculate it. What I took was the radius is equal to the length. Let's start from again. A2 by A1. A2 is 2 pi r square plus 2 pi rl. Now length is equal to the diameter, so I can write L is 2r, right? And this is 4 pi rs square. So this becomes 2 pi r square plus, so 2 pi r square. Remember, r is the radius of the cylinder, and this is 4 pi r square by 4 pi rs whole square. So this becomes 6 pi r square by 4 pi rs square. So this becomes 3 by 2 r square by rs square. So this value 3 by 2, radius of the cylinder is 0.25 whole square by radius of the sphere is 0.5 whole square. So this becomes 3 by 2, 1 by 2 whole square, 1 by 4. This is 3 by 8. 4 2 is 8. So now if I substitute f12 here, it's 3 by 8, f21 is 1, so this is 3 by 8. And again if I substitute in here, so f11 is 1 minus 3 by 8, which is 5 by 8. So let's look at the value for 5 by 8. 5 by 8 is nothing but 0.625, which is one of the option. So the answer for this is B, which is 0.625. So let's see whether 58 is B. Okay, so this how you have to do a problem. So first get A2 by A1, and then so all these problems, radiation, summation and reciprocity, go intact when you have two surfaces. That's it. You have to properly apply this and sequentially solve. Let's discuss 2005. Lot of questions in 2005 from heat transfer. A small copper ball of 5 mm diameter at 500 Kelvin is dropped into oil bath whose temperature is 300 Kelvin. The thermal conductivity of the copper, I am just writing in short form, is 400 watt per meter Kelvin. Its density of the copper is 9000 kg per meter cube. Specific heat of the copper is 385 joules per kg Kelvin. And the heat transfer coefficient is, if the heat transfer coefficient is 250 watt per meter square Kelvin, and the lumped analysis is assumed. Lumped analysis is assumed. The rate of fall of the temperature of the ball at the beginning of cooling will be okay. So 8.7, 13.9, 17.3, 27.7. Okay, so what is given is you have a small copper ball, okay, which is of dia 5 mm. So radius is half of it, 2.5 mm. Okay, and 500 Kelvin is dropped into oil bath, which so this is 500 Kelvin. The oil bath is 300 Kelvin, and it'll try to lose temperature. So all these kind of problems where you drop something, a hot body, into a cooler medium, it can be quenching in air or quenching in oil bath. So these are all quenching related problems. Then at the start the temperature is T naught. Let's say the temperature is T naught. Ambient is always assumed to be 300, and as time progresses this will cool, and we assume that it uniformly cools. Lumped analysis is followed. So the equation that governs at time t is, let's say the temperature is T, so T minus the ambient by initial difference is varies exponential. So this is how your equation is derived, where H is your heat transfer coefficient between the solid and the ambient, A is surface area, V is volume, C is specific heat, rho is density. Now what we want is the rate of fall of the temperature of the ball at the beginning. So basically we want dt by dt. So from this is at any point of time, this is t, small t will be coming, I have not written. So minus HA by rho CV is what I'll get. Okay, this gives the temperature at a temperature of the solid body at time t. Okay, so this is T naught minus T infinity exponential minus HAT by rho CV. Okay, so now I want dt by dt. This is what I want. So when I differentiate this with time, so I'll get on the left hand side dt by dt, and T naught minus T infinity. This will be minus HAT by rho CV into minus HA by rho CV. So this is what I want, rate of fall at the beginning of the cooling, that is at time t0. I want this. So dt, substituting t0, I get T naught minus T infinity. This is e power, t is 0, so it becomes 0. This is minus HA rho CV. So I get minus HA by rho CV, e power 0 is 1, T naught minus T infinity. So let's calculate this. H is given as 250, area is 4 pi r square. So A by V would be 4 pi r square surface area by 4 by 3 pi r cube. So this will be 3 by r. Yeah, and in terms of dia I can write 6 by d. R I can write d by 2, which is 6 by d. So let's substitute like this, minus 250 V B I can substitute d by 6, d is 5 is 0.005 by 6, r by 3, which is okay, and density is 9000, and specific heat is 385. So and T naught is 500 and T ambient is 300. So let's see how much I get once I use a calculator. So I get minus 17.316. okay, and this is Kelvin per temperature or degree Celsius per temperature. Okay, so this is the rate of change of temperature at time t0, but minus here means the temperature is decreasing, and that is what is asked. The minus is included in the question, the rate of fall of the temperature. That means, so what is asked is minus dt by dt, which is nothing but 17.316. The answer for this is, so this is Kelvin per second per time. So answer for this is close to 17.3. Answer is C. So these kind of problems also can be asked. Only thing is the governing equation in the lumped analysis, which initially I figured out, this need to be remembered. Most of the time the temperature at certain point of time is asked, but this is an interesting problem. The rate of fall of temperature at the start is asked. Let's discuss another question from 2005 itself. 59th question from 2005. Hot oil, so this is a heat exchanger. Hot oil is cooled from 80 to 50 in an oil cooler which uses air as the coolant. The air temperature rises from 30 to 40 degrees Celsius. The designer uses a LMTD value of 26 degrees Celsius. The type of heat exchanger is okay, so he uses a value of LMTD, and let's see what this problem help us to learn. So these are the options, guys. Okay, so first thing is oil, hot fluid. It enters at 80, leaves at 50, hot. Okay, and let's first take, because most of the time one thing you have to understand in this LMTD calculation is that the LMTD for parallel flow is the lowest and counter flow is the max. The LMTD values for parallel flow is the min and counter flow is the max, and if it is cross flow it lies in between. So let's first calculate these LMTD values, and then let's first calculate the LMTD value and let's figure out where does it lie. So now for parallel flow, okay, so assuming it's parallel flow, the air temperature rises from 30 to 40. So delta T1 is 50, delta T2 is 50 minus 40, that is 10. So your LMTD is delta T1 minus delta T2 by ln delta T1 by delta T2. So this comes out to 50 minus 10 by ln 50 by 10, which is 5. So 40 by ln 5. So this value 40 by ln 5 is, let's calculate that value, it is 24.85. so this value is 24 if it is a parallel flow, but then the designer is 26, so it's not. So let's now see for the counter flow what is the value. It's always better to determine the extent. So this is 80, this is 50, and this enters at 30 and goes at 40. So this delta T1 is 80 minus 40, which is 40, and this delta T2 is 50 minus 30, which is 20. So here the LMTD value will be delta T1 minus delta T2, which is 40 minus 20 by ln 40 by 20. So this is 20 by ln 2. So let's see what is the value. So this comes out to be 28.853. So the value is 26, which is in between the LMTD of counter flow and LMTD of parallel flow. So it got to be a cross flow, because I mean the counter flow is the maximum, and cross flow where the tubes are something like this, okay, it lies between, the LMTD lies between cross flow. So it's always better to know the range of LMTD. One thing you have to learn is that LMTD for the counter flow is the max and parallel flow is the mean, and for cross flow it lies between. So to check the values, the designer uses 26, that means it's a cross flow. Answer for this is D. Thank you. Let's discuss question number 17. This is also from GATE 2005. Okay, the following figure was generated from experimental data relating, let me write down the question. Following figure was generated from experimental data relating the spectral blackbody emissive power wavelength at three temperatures T1, T2 and T3, and it is given that T1 is more than T2 more than T3. So this is the figure which is given. Okay, black body emissive power. So this is how it varies. This is as per given. So this is T1, this is T2, and these are the peak. Okay, so I mean, whoever has studied radiation would know that this figure is wrong, and that's what is asked. The conclusion from this graph, conclusion is from the measurements. I'm just writing the question in a very short form. Correct, because the maxima, anyhow it is wrong, but just let me write down the options. EB lambda shows the correct trend. Okay, and B is correct because Planck's law is satisfied. C, it is wrong because the Stephen Boltzmann law is not satisfied, and it is wrong because the Wien's displacement law is not satisfied. Okay, so anyhow who has now if you would have studied this radiation, you would know that spectral black body emissive power, when you plot against the wavelengths, it basically varies as the temperatures are increased. The maxima shifts towards the left of the wavelength. So this is how it varies. So this is T3, this is T2, and this is T1. The maxima should shift leftwards. The maxima at higher temperatures shifts towards lower wavelengths, and that's quite feasible. I mean, that's what is observed in the nature. The higher the temperature, the body tries to emit more of its radiation at lower wavelengths. For example, sun, take a light bulb, take a human body temperature. Human body temperature is about 37 degrees Celsius. We emit infrared radiation. Okay, and we are somewhere here. This is the case. Okay, and now if you take an example of sun, which is the temperature is around 5000 Kelvin, it emits mostly, I mean, the ultra violet and in that region. So that has temperature here. Those are lower wavelengths, right? The ultraviolet and combination of visible and some portion of infra and some portion of ultra. So that is towards left. Tungsten bulb, it emits portion of IR and visible, but we emit mostly infra. So it varies like this. So maxima at higher temperature shifts towards lower wavelengths. So here this is what is your actual graph, and this is governed actually by the maximum. All these maximum points are governed by this LM T max is constant, and that is Wien's constant. I think the value is 2987, something like that, but this is how it should behave. So T max, and the point where the T max is observing, that is lambda. So lambda T max is constant. That means as temperature is increased, lambda shifts towards left. So that's why what is wrong is the Wien's displacement wrong is not satisfied. So the answer for this is T, and this is the correct figure. The answer is T.